Okay, welcome everyone, and to this week's compiler architecture meeting. Today, we have one topic to discuss, and it's a sort of an early draft proposal for a new IL intrinsic opcode. We had talked about this, I think, late last year, and sort of the follow-on to that was to kind of come up with a little bit more of a concrete proposal around a new IL opcode. So I've kind of done that here. It's not complete yet. Unfortunately, I haven't had a lot of time to put into writing it, but I'm hoping that some of the rough parts and unknown parts can be sort of filled out with some discussion that we have around the table here. I also wanted to take this opportunity to try out the new IL opcode template that we had talked about, in which there's a PR that I need to get merged, which actually creates it. I'm kind of glad I did that because there are a couple of rough spots with the way that you would write one of these following that template. So
that's the Daryl dash.
Yeah, that's the one that it created my own branch. It created the branch for me. Yeah, that's the one I got to get merged.
You were looking for.
Yeah. Okay. So so to take it from the top, I'm proposing that we add a family of new opcodes for that can represent an intrinsic function. So family being one opcode per data type return. So very similar to a call intrinsic, or very similar to a call opcode. The only difference being that there isn't the notion of a void intrinsic, which I think doesn't make any sense, right? So my thinking
returns nothing. You mean?
Yes.
Doesn't produce a value.
So my definition of an intrinsic is some kind of side effect-free operation that we want to basically get through to the back end, such that it can be turned into either a single instruction or a sequence of instructions.
Do you have an example of something that's side effect free that you would use this for right now?
Well, there are dozens of opcodes in OMR that basically map to arithmetic operations like double exponents or sine, cosine, that sort of thing, that basically live until the back end, and which a back end would actually implement an equivalent for. So in OMR alone, there's about 100. You can probably find more if you scrutinize the tables a bit. But, so I'm hoping that a lot of those could get collapsed down into an intrinsic opcode, a single intrinsic opcode.
And sorry, and you're thinking that if something has a side effect, that it would be better implemented as an actual call to represent that there's a side effect there? Is that the thinking? Or that there's less benefit in not making it a call, or making it different than a call if it has a side effect that has to be modeled?
So, okay, so that's an interesting question. So the thing about a call, okay, take a step back. My thinking was that there actually isn't any function that backs these intrinsics. Always something that the compiler has to deal with in some way. So it doesn't really have the notion of a symbol reference for which there is a function. So one way of perhaps, so when you actually have a call, you need to have a symbol reference. So it would have to be sort of like a symbol referenceless call, or alternatively, we could actually introduce another kind of intrinsic that is capable of throwing an exception or something like that, or have some kind of a side effect.
But having a symbol reference suggests that you can have a side effect, but it does not mean that you do, right? It's down to the aliasing set associated with the symbol reference, right? So I'm a little curious, given that you want to make it symbol reference-less, how you propose to make it easy to read the IL to know what the intrinsic opcode is, right? So if you're going to collapse cost and sin and cinch and everything down, how do we read it?
Right. So One way we could do this is to actually introduce a new enum that describes what the actual intrinsic is. It maps to an actual intrinsic operation. You could union that to the symbol reference on a node, because that's what other nodes that don't have symbol references do. And you could provide this enum that describes these things. You could make it an extensible enum so that some project can come along and add their own list of enums, or a list of intrinsics that it cares about to it if necessary. But it's actually, so it's essentially adding some side metadata to identify which intrinsic we're talking about. The thing about introducing a symbol reference, if that's what you were thinking, was that I think there isn't really the analysis, like it doesn't actually have a function backing it, which is kind of what you'd use that for. And then you'd also have to go and create symbol references for all the different intrinsics that you care about, and which adds to the symbol reference table. And you'd also need to have, adding the different references to the reference table. So,
well, okay, I can see the argument about the symbol reference table, but I mean, there is already a very strong precedent in the IL for symbol references that are not functions that map to, so primarily memory indirect operation, like an offset or something like that, or denote a particular kind of load even when the load is at the address that's specified. Like, I know those are indirect, but some of them also specifically say that it doesn't alias anything and things like that, because, like BFT pointers and things like that. So I'm just wondering what you're going to have the enum anyway, and that's going to have to be stored somewhere, and it's going to take space, right? Like, it has to be in memory, like when the DLL loads or whatever, right? There's a chunk of, you're going to need that list, right? Like, everybody's going to use that all over the place, and I'm not quite sure what the advantage is of making it orthogonal to how everything else is working at the moment. Like, I'm trying to see the benefit of making it unique.
When I was looking at it, I was looking at it more like an add opcode, for example, than a call opcode. So it can be used in the same kind of context, but you would be able to use an arithmetic operator right now.
So just a meta comment here, we seem to have kind of dove down into the details of what this thing is before we've kind of heard any description of why we might want to have an intrinsic IL. So, I mean, is there conscious that we stopped on your agenda slide and we're talking about symbol references, so I just wondered if there's maybe a slide or two that talks about the
no slides.
Why? Okay.
So you can look at the some of the text that's already in the.
Yeah, I hadn't had a chance to open that before the meeting, but I'll go grab that now.
So motivation being that you can reduce. So there's a lot of apparent duplication with these different opcodes, and it's really trying to limit the explosion in the number of opcodes that we actually have by really just introducing one opcode that's got similar properties across all those different opcodes that we have right now. So if you're trying to teach the optimizer about some kind of a new, you don't have to teach the optimizer about some new opcode or update all those tables. You just basically, it's just another intrinsic that's got the same properties as all the other intrinsics that are there. So it's really a reduction in the number of, well, hopefully a reduction in the complexity of that. Said here that you can probably reduce the number of opcodes in OMR alone by about 12%. That's about 100 opcodes. See.
Is that by folding things like an add or a B add into turning into a B intrinsic, or is it by more specialized things?
It was a very specialized, like the double exponent.
I just asked because you mentioned add more like an add before, so I just wanted to see if add was
the point of mentioning add, though, was that it would be slotted into pretty much the same scenarios where you could use an add. It doesn't really have a side effect. You can use it. You don't have to anchor it.
And I guess in theory, I guess the notion would be that the optimizer is unlikely to do anything with this intrinsic. It's a kind of a pass-through for the optimizer.
Other than perhaps simplification, right? So if you're doing, like you can do, I think you could do simplification of an intrinsic opcode if you knew, like presumably you could do, let's say, like a switch on the whole known intrinsics, and if it's like a double exponent and you know that one of the children is 0 or the right child is 0, you could maybe fold that into something, provided that the semantics of the intrinsic are well understood. So I think that there are some optimization opportunities for these.
Doesn't that then mean that we need to know whether a given intrinsic is commutative and transit, whether it's transitive and commutative in its properties or not? Like for mathematical operations, right, the things that you do with simplification beyond sort of mathematical identities, right, you want to know whether the operation is commutative, whether it's transitive, so that you know what motion is possible, right, because that's what allows you to move things up and down across mathematical equations and fold expensive things versus cheap things. So how do you propose dealing with that?
So right now those are properties on the opcode, right?
Or they would be encoded specifically for the handler of that opcode. But if you're going to collapse them all, then you're going to end up with this massive switch. And
sounds like if you want to do any optimization, it should be an IL.
Yeah, that's kind of where I was.
Simplification is an optimization.
That's in the direction that I was trying to lead to.
So this just sails straight through to the back end.
Yeah.
I think it's a little restrictive to say that the thing has no side effects, because I could see a ton of opportunity for mapping actual calls down to intrinsics.
What kind of call? Why would you do that if the call has side effects? You can recognize the call can say.
Well, a call can have side effects.
But why would you change a call to an intrinsic? Let's say you go with Daryl's suggestion that intrinsics don't have side effects. Then you decide I have a call that I want that can map to an intrinsic. Why would you bother to make that transformation if you still have the same, the code generator still has the same opportunity to catch it and do something with it?
well, right now, the intrinsics for the sake of inlining, right? So the methods that we're going to recognize have to be blacklisted in the inliner. And
if you want something to float all the way to cogen without optimizer touching it, that to me is an intrinsic.
Right, because at the moment, there's no way of knowing whether a call is a call, or a call is an intrinsic, or a call is a helper, or a call is some other random thing that happened to be conveniently represented with a call. Well, it's true. They all, well, like array copy answers yes to his call, right? So,
but at some point, the inliner checks to see if it has bytecode or IL or something behind that call.
But there are ones that we choose to map down that do have an implementation because you can do something
like
simpler.
From OpenJ9, Java-Lang map min.
There is a bytecode implementation.
Yeah.
The translation is sucky. There's a single instruction.
Yeah.
Nike would say, just do it.
Sorry, I'm still struggling to think of an example. When would a function like that have a side effect? I might imagine like being able to throw an exception if it has to do like some sort of div check like thing, but
well, it depends if you want to use intrinsics for things like change the floating point mode. That's a side effect.
Mm-hmm.
Also, the
isn't really. I mean, it's kind of a call, but it's not really a call because it's like right now we would use a call for it. It would
Also, the atomic memory operations. People have at various points, like an atomic write, people have said, oh, well, that's an intrinsic, but right now there's a whole family of calls that are recognized as that and mapped down.
Okay, the atomic operations actually make sense in my head.
Well, and the need for a symbol reference also associates with like the even if there are no side effects, the memory model notation about that happens before edges that may be associated with an operation, right, are captured on the symbol reference via like the volatile flag at the moment. So if you were to not do something like that, like right now, that would have to be a call necessarily because of needing to put that on it, even if it has no other side effect other than needing to say that you have to flush buffers.
So, I mean, what I was mainly interested in at this point was really going after the hundreds of IL opcodes that are side effect free. This should pass through to the back end. So if I have to form a definition around that class of opcode, and I'd like to do that. If there's another class that has side effects that we might want to handle as well, like I think if you start doing that, then you also have to anchor them too, right?
Yeah, probably do, but I think that there's a danger in the naming that's being discussed here, that we've already had several rounds of helper versus non-helper versus intrinsic, and now we seem to have overloaded the term intrinsic again to have a more restrictive meaning than we were even planning on using when we were going to rename non-helper to intrinsic, which I'm not quite sure where that leaves our design and naming process. It probably means we suck at naming, but I think that as a collective I am included in that.
Okay.
So for the sake of discussion then, just talking an idea out loud, what if instead of having the notion of, so I know currently what you were just describing about how you would prevent reordering is with this idea of a side effect.
Yes.
What if, so for an intrinsic, we might have something that's a little, that would not be a side effect, but that would still imply cannot be reordered with other things?
You would have to add a special case to all of the aliasing and data flow logic to handle that, right? Because currently the notion of a side effect and the notion of ordering is intermixed with the notion of aliasing in the Testarossa, well, the OMR compiler scheme. And that then means necessarily that if you make any exception to that, you have a sort of a world of hurt. I'm trying to think if there's another word. I keep thinking of affine, but I don't mean affine.
Okay, so maybe to start with, just nailing down what we think the definition of an intrinsic actually is, regardless of whether it's side effect free or not, or what the purpose of the intrinsic is. I mean, that's what it is. So if it is something that we just want to get through to the back end for lowering at the back end, implementation at the back end, and there isn't, at least in my mind, there isn't actually a function that would end up getting called that you would pass along with it. It's basically you're turning this into some kind of a machine instruction. That garbled definition is what I would consider to be an intrinsic.
But by that definition, atomic right is one of those things.
Okay, so
there is no implementation.
So I guess when we start talking about, when we start introducing the notion of these kinds of side effects, that does change the semantics of what you can do with that node, right? Like
I completely agree, but by a definition of, I wish to have a node that will translate into one or a small set of instructions, I think a lot of people, like modulo the math, a lot of people's will be the atomic operations because that's what more people spend time worrying about.
Right. So you almost have a side effect version and a non-side effect version, which is not great.
No.
but then you would have two. So you would have an intrinsic node that would, depending on the properties of the thing that it was representing, may need to be anchored or may not need to be anchored.
Yep. Or there's two classes of things there, things that you wish to anchor and those that you don't.
Right. So, and if we are going to allow it to perform memory operations, then we need a symbol ref. Yes, we need a symbol ref.
If it's going to interact with the memory model, it has to have one.
Right. So how do we decide then whether or not it should be anchored? There would be like a property on the, either the alias information on the symbol reference, or
Either that or we need
the,
two opcodes, two families of opcodes.
Side effect, intrinsic and intrinsic.
Yeah.
Pure intrinsic.
I really don't want to have to write
pure,
that.
yeah.
That's a good word, actually. That's a good word. You really, sorry, what did you really don't have to?
Well, I really wouldn't want to have to write
Pure.
well, side effect.
Whatever they end up-
No.
A pure intrinsic.
Moral.
Dirty intrinsic.
Okay, let's keep the naming for another.
I reiterate my previous statement about our ability to name things.
Yeah, so perhaps having the notion of two different intrinsics, two different classes of intrinsics for side effect free and pure.
Are the 100 opcodes that you've targeted for this initially, do those tend to be opcodes that are platform specific? Like we only use that opcode on x86, or we only use it on Power, or we only use it on Z?
Well,
Are they more platform neutral kinds of things?
no, I think they're fairly floating point specific, and in fact, I don't even think there are implementations for all of those in OMR. Like, even though the opcodes exist, I don't think the backends fully implement double cosine, for example. But the capability would be there to add that, should that be necessary. One of the other things I got coming up is a floating point strategy for OMR, which has been going on for a while. And one of them is to purge a lot of that stuff that we're not actually using at the moment. But it would be easy to add, if we had some framework in place for adding intrinsics, it would be easy if somebody did want to add a double cosine and actually did come up with the actual proper semantics of what a double cosine really means, or well, whatever, and they could easily add that in the future if necessary.
Are there no, I find it hard to believe, are there no math-based optimizations that one might apply to that sort of I get that it would be rare and that only certain people would use them because you only have that intrinsic on some platforms, but I guess I'm wondering about the path where something starts out as an intrinsic because, it's a certain instruction on a certain platform, but then you start generating front ends start wanting to leverage that intrinsic, and it becomes a useful operation. So what happens if you have an intrinsic operation that all of a sudden you now want to turn it into a fully fledged opcode? Like, what is that? If we go down the path of turning this into an intrinsic first, does it make it harder to turn it into a fully fledged opcode going forward?
No. I would argue the opposite, because that's kind of the process an LLVM has. If you want to add a new opcode to LLVM IR, the suggestion is you first try to implement it as an intrinsic, show the value of it as an intrinsic, and then make an argument based on that for why it would be beneficial to have it as a fully fledged opcode, because just an intrinsic, you can't do these things.
Okay.
Right? It gives you a test, it gives you an intermediate steps between not having anything, basically having or call and having an opcode, it gives you stepping ground to make your case for why it would be useful.
All right. Okay.
Sounds like two opcodes, one without a symbol reference, one with a symbol reference.
Yeah. Times 7 for the number of, for the types.
Right.
Presumably, the symbol reference one could now have a void version.
Yes.
And
I think if you're going to do so based on the list of opcodes you've listed, there is specifically not the opcode version of this listed. So how does the vector math fit in with this then?
I have to think about vector because we were going to redo all the opcodes, the vector opcodes. I think Gita was going to owe us a design on that one. I'm trying to remember what we had decided on that one, but so depending on the outcome of that, it doesn't apply to vector at this point.
I had thought maybe my memory's gonna fail me here, but I thought we were going towards a path where the data type expressed the width of the data path, and the operations would indicate the partitioning. Does that make sense? That doesn't make sense.
I thought we had a giant explosion of opcodes incoming.
Sorry?
Yeah, I think
No, but we're doing
yeah,
but only the conversion opcodes was the only place where that became truly painful, I think. So we had a story around the conversion opcode being a more generic kind of only one, kind of like the current typeless model. So you could do a type to a type with only one opcode. But and I know there was a split between integer and floating point because that made sense. But I think there would be an explosion of opcodes. Not explosion, it would get more. We would get many more opcodes.
Yeah. We've got notes on that meeting from like a year and a half ago that have to dust off the.
I guess my point is that there's I hate to say finitely many, but realistically probably finitely many math operations that people will care about enough that they want to implement as intrinsics, right? Like, okay, you need all the trigonometric functions, you need the hyperbolic trigonometric functions, you need, whatever. But the areas where people will really be pushing on things in terms of exploiting hardware and stuff like that, most of the new opcodes are all related to vector operations or algorithm implementation.
Crypto type stuff.
Yeah. And if we're going to have intrinsics, having some story for that.
Yeah, I don't want to preclude that's for sure. I strongly suspect that we would have an intrinsic opcode before we renamed all our vector opcodes. But I could be wrong. But anyways, yeah, I agree. We should have some consideration for vector when we remember what that is.
So what's the thing driving this in the notion of introducing intrinsics?
Partly to as part of the general overall IL cleanup. So by squishing it down to really the smallest set that we really need, especially in OMR. Right now the set is probably over 900. With just the ones you can eyeball, you can squish that down to probably about 800, maybe more. But yeah, it's really just driving simplicity across the board. Okay. So if we were thinking about two different ones, one with a symbol reference, one without. The one without, so your concern is still with the one without, and how do you identify the operation?
Well, yeah. So I mean, the proposal to go and create a union around the symbol reference.
It's not creating a union. The union already exists.
All right. Well, adding jamming yet another thing into that union. Right. It's just around how is the code going to look surprising because it's this weird thing that doesn't behave like anything else. Now, yes, they're intrinsics and whatever, but given how other things are currently implemented, are we saying that we're going to do this because this is how we want other things to be done, or are we doing this because we think it's convenient? Or I guess is my question. I'm not really decided myself. I'm just asking the question.
Yeah. Well, I mean, this isn't a justification. I was thinking aloud. So if you knew that the opcode was an intrinsic, you would presumably have a function on the node that, as we do for every other kind of opcode, that basically says give me your intrinsic name or whatever, or opcode value. That's not the right word, but and it would dig out the appropriate intrinsic number for that. I don't know. I mean,
and I can see the attraction in one sense. I also struggle with it in another sense.
Well, in one sense, we're creating a dual kind of opcode, right? It's like a different kind of opcode that indicates what its operation is, using a different field on a node to tell you which it is.
Yeah.
So the fundamental question for me comes down to, is there really enough value in reducing the number of opcodes to the point? I mean, I still have to be able to look at the set of intrinsics and understand what all the different intrinsics are.
Mm-hmm.
So is there really enough value in that list of operations not being part of the opcode set and creating this kind of side notion of this is a different kind of opcode that only uses one opcode, but you have to go look over here to find out what it is? Is there really enough value in doing that to the opcode set, right? I mean, this is another way of looking at this, which is, okay, it's a little bit mind-bending, but bear with me for a moment, right? You could argue that what we did with vector opcodes to try to introduce typeless opcodes there is an example of this same kind of thing, right? We decided not to use opcode as the way to differentiate what the operations were. We decided to put another field somewhere else that, in that case, you could derive from arguments and et cetera, et cetera, et cetera, to represent what the operation actually is, right? And to me, that seems like a move towards less consistent in a way, right? Like the whole optimizer and compiler is built around the notion of, if I want to know what the thing is, I look at the opcode, right? And that's kind of entrenched throughout the whole compiler, notwithstanding that we've overloaded a bunch of calls and done weird things that have had other side effects in the optimizer with the amount of code you have to write in order to figure out what exactly is this thing. This is another example of, in a way, a special case where you have to write a bunch of code to find out what exactly is this thing. That's not just as simple as asking the opcode what it is.
So
I'm not drawing any conclusions yet. I'm just drawing an analogy.
Right. What you're describing is a flat opcode space where meaning of everything is right at the top layer, and
well, I'm saying that's another simplification that you could consider in the compiler, right? Is opcode tells you what the thing does, right? And that's a principle that you could apply to how Testarossa, how the OMR compiler does represent operations.
So I think what you might be arguing then is that there that you should just represent this with a symbol reference then, because how is that any?
I don't think that was my argument.
No, but
I think the question is pushing on whether you're going to collapse them at all. And I think one question that I have in my head is what is the rule going to be around code generator support for the intrinsic list, right? So if you're going to implement a backend right now in OMR and it's going to be correct and supported, basically you have to implement all of the opcodes, right? Like in general, that would be for the trill test to pass on your platform modulo, the ones that aren't tested, right? You're going to have right? The ones that we aren't using but are there, but we should use, and modulo that.
So I don't think that the opcode, an intrinsic should be created for something that a backend doesn't support. So you would need to ask the backend whether or not it actually supports expanding this intrinsic. Like there's basic support for the intrinsic opcode, but actually, you would ask a backend, do you support double cosine?
So you mean when the IL is being generated, you would ask the IL generator. That makes sense to me, to query the code generator to say, hey, do you support this particular intrinsic? And if you don't, I'm going to blow up or something like that.
Well, you can always...
I'll avoid using that intrinsic.
Either avoid it or, pull the ripcord. And like we do in
blow up.
unsupported. Well, blow up doesn't mean, it means fail gracefully.
Okay.
Blow up gracefully then.
You want a pretty explanation.
Okay.
We'll put a bow on it.
Kaleidoscope, yeah.
I apologize for the imprecision in my language.
So,
but I mean, but what you're not saying is that in the OMR compiler, you'll probably have some set of intrinsics that are defined that come along with the OMR compiler. And what you're saying is there will be some code generator for each one of those. For each one of those intrinsics at the end of the OMR compiler, there will be some code generator that will generate that will be able to handle that intrinsic.
Ideally.
Just kind of the same rule we have with opcodes, I hope.
I mean,
unless we have any opcodes that no code generator.
Yes, I think that's true.
We do.
I think
there's like this list, for example, all those mathematical operations. I don't think the existing they came
so
from.
We don't actually have a code generator that will generate those.
I don't believe so.
They probably come from line where you have a function backing the
or they came from a static language that.
I think the bulk of the unimplemented ones are not from Java. They were added when other languages were passing through this compiler at one point, and then that stuff was jettisoned.
Right.
Yes.
Okay. So
so we could either.
So in principle, we could just get rid of those. In principle.
Yes, but I was thinking about a little bit more. Yeah. At least introducing some kind of maybe a better way of handling these things in the future is sort of what I was. So that we have that facility in place in case somebody does come back and say, I really need that double exponent 2.
Right, but...
Okay, that doesn't the extensible nature of the opcode set, how great it is.
Okay, but the question then is, why do you want a separate opcode for all of those different... does the optimizer really need to know about all those... I guess if... Going back to the other ones, if you wanted to...
What's the problem with it? What's the consequence of having a... do I really want another intrinsic enum value? It's kind of the same question almost. And I get it's harder to add an opcode than it would be to add to an enum for an intrinsic list. But that's also a problem we could choose to address rather than building this new... I'm not arguing for a particular case right now. I'm just trying to play devil's advocate a little bit. But this is going to be work to create.
Yeah.
Another place that we could do work would be to try to make it easier to add a new opcode or to change the opcode set without, having to go and update quite as many places, for example, say, I don't know. And then at that point, the difference would be update that enum here or update that enum over there.
Well, so one potential difference I see, and I don't know if this is covered by what you're proposing, but in my mind, the idea of an intrinsic is that it would not be at the same level as other opcodes, it might not get as the same level of optimization applied to it by the optimizer. So there would be a trade-off there where if you add a new opcode, you may have to teach the optimizer about these other things. And in that case, if you actually want to teach the optimizer about these other things, it makes sense to add it as an opcode. But if you just want something that's like, you don't really care what the optimizers, you just want the optimizer to ignore it, having an intrinsic mechanism can make adding that kind of operation easier.
But I don't have to write any code to optimize something if I don't want to. In fact, there's lots of opcodes that are kind of in that space. So
yeah, it's more the opcode dispatch tables would need to default to have.
so that's the kind of thing I was getting at. Like there's an engineering cost that we have right now to add an opcode, which is making us fearful of, or trying to find alternative mechanisms so you don't have to go and update a whole bunch of different places when you add an opcode, right? But if that were the problem we solved.
Right. I guess what I'm wondering
you don't have to, if you're adding a new opcode, you don't have to go to 8 different tables or whatever the number is these days and go and, add an entry into the table in the right place, blah, 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 blah.
I guess what I'm wondering is that even possible?
Well, sounds like a very pessimistic kind of viewpoint.
Well, I'm just thinking about it from other compilers I've looked at, LLVM being the obvious example, where the reason it supports Intrinsic is to make it easier for people to add these custom operations without having to add a new opcode, because that requires fiddling with the optimizer so that it doesn't choke on it if it sees one.
Right, but the argument against looking at the LLVM model is the very fact that Chris Lattner has created MLIR and that they're doing successive lowering.
Right.
And if, let's take the trigonometric functions as an example. If you wish to optimize trigonometric functions, you're either going to have to extend an existing optimization or write an optimization that's going to do something sensible with them. And at the end of the day, the implementation of that, is either going to end up being a call to a math library or an instruction. And depending on the platform, it's going to be one of those two things, whether you have hardware support or whether it's software emulated. So if if what we're talking about is that there's a domain of operations that a majority of OMR users don't care about, but that a subset of users do care about, then a successive lowering notion is a much more useful notion, in my opinion, where they can do the stuff they want at the higher level, and when they're done with it, if we're going to support particular math operations, the logical extension point for that at the moment, in the way everything is engineered with minimum fuss, is that it is a call, because the call may be genned as a library call, or it may be genned as an instruction, and the choice on that may not even be fixed for a given code gen. It may depend on what the operating system has configured. It may depend on a variety of things as to what the code generator would pick to do with that thing, And the notion is, well, it could be side effectful because it may go off and run some random block of C code, and we have to be careful about that, and therefore representing it as a potentially side effecting thing that the rest of the optimizer should be conservative about in the grandest OMR sense makes the most sense, And that if you want to have these other properties, then you should have an abstraction at a higher level that you then lower to this when you're done with it, And that's the whole argument for MLIR, for the TensorFlow dialects, and all that stuff. So, and I think that there's a proof point there that says that somebody has had a lot of success with that, and we've fought to try and extend the opcode implementations a lot, and it always proves problematic. Because at any given layer in the abstraction, your optimizer must necessarily understand all of the opcodes that it's dealing with. Otherwise, it's essentially just going to have to ignore a bunch of stuff and treat it hyper-conservatively. So if you go with successive lowering, well, then we define at the OMR level the common currency. And if enough people care about cinch, we'll add cinch and do whatever we're going to do with cinch. But, the chances are that there's going to be some math people that care about it, and they'll do all their mathy stuff on it, and then they'll lower it. And it'll just turn into a call or whatever it would at the moment that, will get genned. Right. So I think, I'm not saying that we should necessarily go with that design, but given that that is one direction that a very large community of people are going in after a lot of wrangling with a big compiler framework, there should be a consideration as to whether that is the right way for us to go.
That's a good point.
To make it easier to add languages to OMR, where if you can define this higher level thing, you write optimizations that work on that higher level thing, and then lower it, and we could then conceivably add like the MLIR feature where, okay, CSE, for example, you can provide a definition of some kind that then CSE can consume, and it can do certain things to your opcode, right? And you can just run it. But pretending that the OMR optimizer is going to be a fantastic math optimizer, I think is a bit of a fallacy, no matter whether we do it with intrinsics or not. It's always going to be a problem.
This discussion would have been easier to have if we actually had an opcode or an intrinsic that somebody was proposing and they wanted to get it in. That way they could evaluate the pros and cons a little bit more
Concretely?
Yeah, in a more concrete way, because they're in a position to write code and
Hold that thought.
they have a
Here it comes.
if there's somebody out there.
So we have a ton of functions that we map in OpenG9 as just calls, which we blacklist from the inliner, that are all intrinsic candidates, had we had an intrinsic.
So it might be a
I could certainly see that for strings, for example, in Java, we go to an incredible effort at the moment dealing with string builders and concatenation and all kinds of stuff because of the IL representation necessarily being super low level. And just like Latner's proposal around std vector for MLIR for Clang, which is not actually being built, but slideware is awesome. Having a higher level IR that describes the strings and the operations on them so that you could actually do these things without having to walk layers of calls and anchor children and stuff would make a load of sense. And then OMR doesn't care about the semantics of, possibly 8-byte, possibly 16-byte characters and all the other gorp that goes with that. We just lower it later, right, and feed it through. Right?
That makes a lot of sense.
So, I mean, there are ways I could see it being used. Now, whether it's the right way to go, I don't know. But I think it's a design point to consider.
But at that point, you're almost talking about a pre-ILGen world that doesn't exist right now.
Well, no, I think I think that the ILGen changes to use the higher level abstraction. So the OpenJ9 code generator, when it sees like a string builder create or an append or something like that, is actually going to do string append of an object and an object, right? Yeah. And you have a string append opcode. And when we're done, we run optimization passes ahead of the main optimizer where you go and manipulate that stuff. And then when it's done, you lower it, right? And
right, I guess my point is that lowering step is essentially what we think of as ILGen right now. It's just not ILGen from a bytecode set, it's ILGen from that higher level description of the operation.
And MLIR does have that property. Right. They do that, right? And in fact, some of their IRs have like 4 or 5 code generators that essentially are ILGenning to another representation.
I feel like we're a little bit afield from.
I think we're afield from it, but I think I
understand why you bring it up.
Yeah.
Just picked a couple of these, like double hyperbolic cosine. It's only supported on Z, and what happens is it sails through to the back end. Nobody touches it. The back end then creates a call node, and then
successive lowering. What did I tell you?
And then evaluates it.
Holy deja vu.
I don't know where the symbol comes from though.
Probably
somewhere.
It's calling a helper, right? So it's
There must be a symbol reference on that because it's just called, it's got to be on the node when we create the double.
Yeah, well, it would just be a helper simref that doesn't even necessarily have a symbol behind it, right? We have that.
Here's a bag of symbol references. Pick
Yeah,
one.
right. But it's being successively lowered already at that point.
So that's an example where we chose to use an opcode to represent it through the whole optimizer, and then it turned into a call.
Because it might side
as
effect
opposed to
because
the
it
other
might
option, which would have been to represent it as a call that got blacklisted by the inliner and passed all the way through the optimizer as well.
Well, the call
Where the
doesn't
difference
have,
is that the call would have necessarily anchored, whereas the node may not have necessarily anchored.
Yes. That's the major difference there. But
So there is your side effect and side effect free examples. So if we're going to build something, it sounds like we do need both, because there are examples certainly in the other camp. It does mean we need both kind of categories of these things, it sounds like.
Yes.
And then I guess the question
so we
is,
go back to, how do we represent them pure? Is there a symbol reference that is like a pure?
I don't remember there being the notion of a pure call.
Yes, it's a flag on a symbol reference.
Flag.
there you go.
But you need a symbol reference to add that.
Right. Like the mathematical operations in Java, for example, at the moment generate symbol references, but there's a white list that adds a flag that tells the optimizer that it's side effectless from the point of view of aliasing analysis and things like that. So for escape analysis in OpenJ9, for example, that flag will tell us that you're not going to escape. You're not going to violate the rules around a call in that a call must be anchored, but it means that optimizations that would necessarily, intersect their alias sets and all that kind of stuff will ignore the node, right? It will basically just say, no.
But an opcode that has no symbol reference on it that the optimizer doesn't know anything about is, in essence, pure anyway, right?
Yeah.
Because the optimizer won't believe that it changes anything. It will feel free to let it lie wherever it lies.
Yeah, absolutely. No, you're exactly right with that. And I mean, if you added the one without the symbol reference,
right.
We can just add the dummy entry that says do nothing, constrain children, whatever. And I think that would be the sum total of it. I think the slippery slope is where you start to examine what the hell that thing actually is, anywhere outside of the code generator. That I think is a line that if we decided to go down this route, we would say would not be crossed. If you're going to look into it, it's not one of those things anymore.
So for the pure intrinsics, you would prefer a symbol reference to be used that's flagged appropriately?
So
and the symbol reference you could indicate the actual intrinsic that you want it to represent in that symbol reference.
That would be one way
I'm not
to do
sure
it.
I followed that completely. Can you say that one more time?
Well, so if the means by which you want to indicate that this is a pure intrinsic is through a flag on the symbol reference, then for a pure intrinsic, you would have to create a symbol reference. And if you had to create a symbol reference, then the reference would be used to identify the actual intrinsic that you wanted to present. Duh.
Right.
Does that make sense?
That time I followed it, yeah.
Okay, good.
So the argument for using an enum was to make writing code that was going to operate on these intrinsics and somehow neater, easier, and possibly save a little bit of space from having the extra symbol references added to the symref tab, right? If the symbol references are added to the symref tab lazily, they will only be added when they're actually used, right? Which is the current find or create pattern. And if we're not actually going to introspect them, if that is verboten outside of the code generators, then adding a feature specifically to make it easy to introspect them seems to be not something we should do because it tempts people to do something which we wish to forbid.
And wouldn't this actually be a known symbol? Not sure what the right term is. So like a known symbol reference in the sense that it'll be one of the predefined numbers of symbol references.
Yeah.
Which means
Well, there's a block.
it will count for something in the table, right? Whether you use it or not. Like if we have 256 known symbol references, we don't start the on-demand ones until after that.
I think some of that comes down to engineering. There may be something we can do there as well. I mean, if the point of the enum is to make it easy to look at the things, and we don't want people to look at the things, why are we going to make it easy to look at the things? But I mean, if it makes sense from an engineering point of view, sure. I mean, it's not going to clutter up the optimizer, so it's only going to be.
Sure. What you're talking about the enums?
Yeah. Well, I mean,
union with the symbol reference.
No, well, if you want to union the enum into the symbol reference slot, and that's what you want to do to represent these, I guess sure. I mean, I'm just trying to look at uniformity in how we do stuff, and one of the arguments for the feature was that it would make things easy, but we don't want people to do that. Therefore, it shouldn't be easy. I know it's a bit of a facetious way of looking at it. But
okay.
Would we not have two different ways of figuring out what is intrinsic?
I have to know. I have
Thanks for your input, Andrew.
Yeah. For pure versus side effect.
Sorry, I didn't hear the first part of your question.
So for pure versus side effect intrinsic, wouldn't we have two different ways of seeing what this thing is? If you have this side table thing, side enum, one would have a symbol reference, you'd query what the symbol is, and the hard-coded symbol is the intrinsic versus.
So if there are two different opcodes, then, I mean, we already have the notion of there's like a million methods on Node, depending on the actual opcode that answers the question that you want. So presumably before you ask that question, you have to ask, what are you first? Like, are you a bound check? Are you a pure intrinsic, that kind of thing? If the answer is yes, then you ask the question you want to ask. So I'm thinking it'll just be different questions on the node, won't it? And how that gets implemented under the covers depends on the opcode of the node, just like every other. You get it, don't you? Yeah, okay. Yeah.
All right, I'm not asking.
Yeah.
I'm listening
over
as
there.
part of the.
But the side effect intrinsic would be, and it would have a symbol reference, and the value of the symbol is what you would query against. Right? So say I have, I don't know, a symbol called, I don't know, intrinsic cosine or something, and you would put that symbol on the symbol reference of the side effect node, and then to query the side effect node, whether it's this particular intrinsic underscore cosine or whatever, that would be the value of query against the symbol, right?
Yeah. There is an asymmetry there.
So you would have a symbol in one case and then this other random side enum thing for the other one.
Well, the thing is, it's sounding like we'll have to have some sort of asymmetry if we want that intrinsic enum value to be in the symbol reference slot, because it can only either have that or the symbol reference.
Yes. But yes, and I mean, if we're thinking about two different opcodes, then maybe we should be thinking of this as two different problems.
Okay.
Which means that the asymmetry is potentially justified.
I hear all this, and then it's going to turn into, well, we'll just create some accessor thing on the node that figures it all out, and so the rest of the compiler won't have to care. And that means that this whole way of representing intrinsics one way or the other are different than the way that we're currently representing it is all for that function that sits on node that everyone calls to ask what intrinsic is this. And that makes me question really a lot easier. Like adding a new intrinsic is just putting a name in an enum or creating some kind of symbol reference. Easy to create symbol reference that represents the.
Okay, both cases the answer would be yes. That's all you would have to do, and then implement it in the back end.
But is that enough? Is
yeah.
Like that's the basic value prop, right?
So
you're making it. You're coming. Let me describe it in a way that you might find less charitable. You're coming up with a new scheme to represent internally what a certain set of operations that you're calling intrinsics, that the rest of the compiler largely won't be forced to understand why that's being represented differently than other things that are like, these concepts already exist, right? Mm-hmm. We already have intrinsics. We have a bunch of opcodes that are pure. We have a bunch of call nodes that people are creating which have side effects, right? Mm-hmm. So there's a solution in place right now. We're proposing a change to how we represent those kinds of opcodes and calls, which on the one hand, all you do is collapse a bunch of opcodes into one opcode to represent the pure ones, and you take a call that has a symbol reference and you convert that to another type of opcode which has a symbol reference, right? So the difference between where you're trying to go and where you are doesn't feel very large to me. I know that's an unfair statement to make, but when you portray it that way, it doesn't sound very different, right? And then the complexity of figuring out which thing you've got, you already have to, in order to avoid having to make billions of changes throughout the code base, you have to make some smart function on Node or somewhere that knows how to access the difference between those two things, right? Which means that it's only that function that actually sees the benefit of representing intrinsics in this new form. So that cost, or that you have to convey against the whatever other benefit you're going to get by changing this whole representation for intrinsics, right? And I don't know. So I think we should explore what that value actually is and whether this is the only way to reduce the cost that you're trying to, the approach that you're taking to try to reduce the effort of adding an intrinsic-like thing. Because in the end, why do we have to make it hard to add new opcodes? Right? Does it have to be that hard to add an opcode to the compiler? And why do we have to accept that it's that hard and that's as hard as it's going to be, and everybody should have to do that much work to add a new opcode to the compiler, even if they're not going to optimize it immediately, right? So we're choosing not to solve that problem essentially, right? And instead, for a certain class of opcodes, we're deciding to do a bunch of work to try to make it easier to add those kinds of opcodes. Are those the most important class of opcodes that people want to add? Maybe they are, maybe they aren't. I'm just kind of trying to explore the space here a little bit. Mm-hmm. I'm going to have to leave shortly, so having thrown that grenade into the room, a series of grenades, I mean, in the end, I'm certainly not invested in the implementation that we have right now for this. Yeah. But so I'm not trying to argue for status quo just because I think status quo is the most brilliant thing on the face of the earth. That's not the case. But right, I guess there's the way I'm seeing it, it looks like there are different ways that you can invest to solve problems that would have similar kinds of effects. And I guess the question is, what's the right one to target to maximize the improvement, right? So if you improve how hard it is to add an opcode to the optimizer, that has the potential to improve lots of people's lives. If you're going to focus primarily on making it easier to add intrinsics, then that's going to help people who add intrinsics, which may be a very important class of opcodes that get added to the compiler.
Well,
like maybe that is the right trade-off.
Well, I mean, I guess, another thing that might weave into this as well is sort of the philosophy behind the IL in the first place, and whether or not we want sort of a maximum IL, or do you want a minimum set of IL? I think we've kind of kicked the tires, not much in the past on that. I'm more on the minimum side than adding more opcodes.
Okay, what's the problem with more opcodes? Is it size of the few tables and just the number of things that we have?
I think I think that sometimes the danger we've gotten ourselves into with by adding opcodes is that we've added opcodes that everybody needs to deal with. Sorry, that's not the right word. Everyone needs to be aware of for only a very limited either project or architecture.
Okay.
And so it's just the presence of those. Not that it's causing any problems, because you can certainly work around that, but it's just the added because there is overhead associated with adding an opcode, not just to the front end, but also to the back end as well. Like the code generator, for example, needs to add some kind of default handler for those opcodes, even though it's nothing, but you have to expand the size of the table. So there is an awareness that you need to have of any additional opcode. So
I think my gripe with, I guess my answer to your question is that we don't have a way to query whether an opcode is supported in a generic way. So I don't know whether I can use
be hard
an
to
opcode.
add. I mean, if we're going to add a facility that can add whether an intrinsic is supported in the code generator,
Yeah.
presumably that
Yes.
same thing could be implemented for opcodes.
Yes.
So
Wouldn't that be just as easy as looking in the opcode, the evaluator table, and if evaluator
is it a bad IL opcode? Or is it,
unimplemented or bad or whatever.
right?
I've never thought of it.
that's how they implemented it in the test compiler, actually.
Is it?
Right. So anyway,
I agree, though. I think we should centralize and look at how to simplify adding of an opcode first, which is an exercise we should do anyway.
right.
Yeah.
Yes, I certainly agree with that statement.
And right now, it's a breaking operation for downstream projects too.
Right.
Because
You're going to do that anyway. If you're going to get rid of all these opcodes, you're going to change the opcode tables, and they're going to get broken. Right?
yeah, but I mean, in the future, if you want to add a new opcode, if you can do it in such a way that you don't break everything by adding your opcode, then maybe that's
Yeah, I think we should implement an opcode and see what all the changes had to be made, and then think about how we can shrink that down.
okay. I'll implement an intrinsic opcode.
Documented in one file.
Yeah.
Used to have this set of
It
if you're adding an it's
yeah.
an opcode number or whatever, right? If you're changing this, go and change these other files too.
That comment might still be there. The paths might be stale.
Yeah. I wouldn't be surprised.
Well, the way people usually do it now is you grab one of the existing unusual opcodes and just grep for it, and every place where it sort of shows up is really where you have to make your change, right?
Right.
So
all that says is we haven't really invested in this area in a while.
No.
grep is our main tool for.
So if the more general problem here is improving the means by which you can add a new opcode and then queries whether or not that opcode is supported by a particular backend, that's a bigger problem.
But one we need to tackle anyway.
Yeah.
Likely.
Yeah.
And I think you're going to run into many aspects of that trying to implement something like this anyway.
Okay.
I would guess.
Okay.
I might be wrong.
How much of a stomach do you have for removing some of the opcodes that we currently have? that are obviously unused, as opposed to actually making them intrinsic, just purging them. And then if someone does,
Well, if nobody's using them and they're not doing anything particularly useful, they're still in our history.
Yep.
There's some, we can document the ones that we've taken out in the past, maybe, and when they got taken out in an issue somewhere, maybe. I don't know. I doubt anyone will ever go and look at it, but in principle, the history is there, and people could resurrect anything that they needed, right?
I would argue that we've already had several proof of concept integrations of the OMR compiler technology into projects, and we've run into opcodes that we once upon a time removed, and then now it turns out we need them. And I can tell you some of those opcodes you're talking about removing are not those. So I would say if we haven't encountered it up until now, we're very unlikely to encounter it in the near future.
right, you're talking about like the byte swap ones and the...
I like your
LED.
optimism, but I'm not sure we've had enough proof of concept projects built on top of OMR to be able to categorically say no one's going to come around looking for this thing.
Maybe no one's.
But
You're right.
But I mean, you're right. We have that OMR compiler has been used in a number of very different scenarios and
Yeah, I guess
platforms. So
what I'm thinking of is at one time when we open sourced the technology, we were trying to clean things up, and we kind of started removing opcodes indiscriminately without thinking too much about whether they would be needed. And some of those, it turns out we've needed them.
yeah, we've wanted some.
So my other argument for actually removing opcode is that we also have this effort to actually document the IL.
Yeah,
and
that makes that job easier. I get it.
Right, and if you want...
Right, I get it. But if you're going to move from I've got an opcode to I've got an intrinsic enum, you still have to document that. So.
Right. So, but I think if I'm moving past that, so there is potentially the notion of adding it up. There's also the perhaps we should just purge a lot of those opcodes in the first place and not even make them intrinsic. But intrinsic is more of a means to, if somebody wants to add them back, what would be an easy way for them to do that? But maybe, I don't know.
I think
Some more
the answer
thought.
to that question should come after we have taken a look at how to make adding opcodes easier.
Yeah, perhaps. Yes. Okay. So I think
I have to run.
Yep.
This has been a great discussion. The most fun discussion I've had this week. So add that to your list of successes.
For whatever it's worth.
Thank you.
Okay. Anything else you guys want to? Any other points you want to make or anything like that? No. Okay. So right. So there'll be some follow up there then. We'll come back to this meeting at some point and report on that. Okay. Thanks everyone for your input, and we'll close the call now. Bye.